Welcome back. This is Steve Denenberg. In this video and the following one, we will work a few problems that have to do with distance and velocity under constant acceleration. As we work these problems, it may look as though I'm spoon-feeding the process to a second grader, but it's exactly how I do these problems myself. The foundation you get in writing down and carefully working with the equations will serve you for all of physics. So let's get started. First problem. You have a block that is sliding friction-free along a plane at a constant velocity of v sub naught. And it's heading off in this direction. And it's cruising along at its constant velocity because there's nothing to change its velocity. And then, during a certain period of time, it undergoes an acceleration, some mystical field. The acceleration is a, and it undergoes that acceleration for a time t. And then it passes out of that area, and it continues on its merry way on this friction-free surface at a constant velocity of v1. And the question is, what is v sub 1? What is its new velocity? So let's not overthink this one. We already know that velocity equals acceleration times time. The speed you're going is your acceleration times the time that you were accelerating. Or, let's be a little more rigorous about how we write it. V sub 1 equals v sub naught plus at. Or the way I like to do it is v sub new, your new speed, is your old speed, v sub old, plus at. So if you start out with a certain velocity and you undergo an acceleration for a certain amount of time, your new velocity will be the old velocity plus the component of the new velocity, which is acceleration times time. So this is our answer right here. v1 equals v0 plus at. See, that was a simple problem. Let's talk a little bit about these subscripts too. You're going to see v1 equals v0 plus at, or they may write it as v2 equals v1 plus at, if v1 is where you started out and 2 is where you ended up. Or they may say v final equals v initial plus at. And then we have it how I like to do it, which is v new and v old. But it doesn't matter what the subscripts are. What matters is that you understand what's going on. And in fact, let's write it one more way as they do. This is exactly what you will see as one of the equations that are given to you at the beginning of the AP test. It'll say Vx equals Vx naught plus Axt. And what they're doing here is a couple of things. They're making it clear that we're talking about the velocity in the x direction, and we're talking about the acceleration that happens in the x direction. And this is your original velocity in the x direction. This is your final velocity in the x direction. And the velocities in the x direction are only affected by accelerations in the x direction. And in fact, we're going to get to a problem in a little bit where there is an acceleration, but the acceleration is not in the x direction, so it doesn't affect the velocity in the x direction. And if those were too many words, then back up the tape a little bit and listen to it again. Now, next problem. We're going to take a similar situation, but we're going to change it up a little bit. Once again, we have a friction-free plane, and we have a block that is traveling at v sub naught at a constant speed along that friction-free plane. And now, in a certain area that has a certain distance d, while this block is chugging along through that particular part of the plane, that distance d, it undergoes an acceleration a. And now we want to know what is the speed of the block, we'll call it v1, after it undergoes that acceleration. So in this problem, we are not undergoing an acceleration for a particular amount of time. We are undergoing an acceleration through a particular distance. And so we don't really care how long it took to go through there. And in fact, at the end of the last video, we had an equation. And I will write down for you the equation that we had. It's that v1 squared equals v0 squared plus 2ad. The new velocity equals the old velocity plus 2 times the acceleration times the distance through which that acceleration was applied. So this problem also does not require a lot of 8th grade algebra. In fact, I think I just wrote down the answer, that the new velocity squared equals the old velocity squared plus 2ad. That was easy because we knew we had this equation that didn't involve time, and we had a problem here where we didn't particularly care about the time. Now let's take a look at exactly how they write that equation in the equations that are given to you at the beginning of the test. And we'll explain that. And the way it looks is it looks like this. V sub x squared equals v sub x naught squared plus 2a sub x times x minus x sub naught. And that's the exact same thing, but let's just make sure we understand it. First of all, they're just saying that we're talking about in the x direction. If you want to run this in the y direction too, you can run it in the y direction. But an acceleration in the x direction won't affect velocities in the y direction. So this is the initial, that's what naught means. This is the initial velocity in the x direction squared. This is the final velocity, okay? And why are they saying x minus x sub naught? I said d. I said plus 2ad. And here's what they're saying. They're saying that if you have this plane, drew a line, and you have a block that's traveling at v sub naught, and it goes through a certain distance, and you want to know what the speed is afterwards, instead of saying that it traveled for a certain distance, they're saying what is the difference between x and x sub naught. So they're saying that at some point on this x-axis, x sub naught, the acceleration started, and over here, this is where you are. Let's call this x sub 1. So in our equation above, actually, let's go back up here, we can say x sub 1 minus x sub naught. You get it? X sub 1 minus x sub naught is the distance under which the acceleration was applied. I just called that d. They're just saying pay attention to where the acceleration started and where the acceleration ended, so you know through what distance the acceleration was being applied. All right, next problem. We have a plane and we have a ball. And we are going to launch that ball vertically upward at a speed of v0. And it's going to rise upward against gravity, and then it's going to come back down. And the question is, how high will the ball get before it comes back and comes down to the ground? Well, let's take a look at that. we have an equation here. Distance equals v sub naught times time plus 1/2 at squared. Remember that? That the distance something travels is its initial speed throughout the entire time it was traveling, plus half of the acceleration. We had drawn a little trapezoid for that before. Remember that? Under the velocity time curve, this is v sub naught, and this is t. So this is the distance that the ball is traveling because it had an initial velocity, and the 1/2 at squared was the distance that it traveled because it had a velocity that was increasing at a certain acceleration beyond its initial velocity. So this is the equation that we're going to use here, but we need to know what t is. We know v sub naught. We know what acceleration is. That's our 10 meters per second squared because we're talking about gravity here. If we know what t is, then we can figure out how high it got. Are we all okay with that? Well, we do have a way of coming up with t because something's velocity, okay, equals its initial velocity plus the amount of time that it was accelerating. So this little ball is going to start out with an initial velocity of v sub 0, and then gravity is going to cause an acceleration through a certain amount of time to stop its upward moment. So we are going to have to be better about signs now. So if we say that v sub naught is positive in the upward direction, let's say it's 5 meters per second, okay, then we have to say that gravity is downward at 10 meters per second squared, because the pull of gravity is going to be opposite of the initial speed of the ball. So let's say that the speed of the ball equals its initial velocity, which we're going to say is 5, but I like to work with letters and plug the numbers in at the end. And we're going to say minus g times t, okay? Because minus g is the acceleration that the ball is going to be undergoing. So let's work that out. We are looking for the amount of time that will cause the velocity to be 0, because the ball is going to go up and slow down, slow down, slow down, and it's going to stop. And when it stops, its velocity is 0, and that's what we're looking for. That will give us the amount of time that it rose. So if we say that v final equals v initial minus gt, and we want v final to be 0, we say 0 equals the initial velocity minus gt, and that means that gt equals the initial velocity, and the time that it takes to rise equals v sub naught over g, over the acceleration of gravity. Does that sound good to you? All right, so now we know how long the ball was rising. You know, I mean, just in general, come on. If you throw a ball up at 40 meters per second, and the pull of gravity is 10 meters per second squared, then every second, the speed of the ball is going to drop by 10 meters per second. So after 1 second, it'll be traveling 30 meters per second. After 2 seconds, it'll be traveling 20 meters per second. After 4 seconds, gravity has eaten away at the entire 40 meters per second, and the ball will stop. And that's all we're saying here. So we know that t equals v sub naught over g, and we know that a distance that something travels when under a constant acceleration is its initial velocity times the time it travels plus 1/2 at squared. And now we're going to rewrite that because gravity is pulling in the opposite direction of the initial velocity. We're going to say distance equals v sub naught times t minus 1/2 g t squared, okay? And now we're going to take the t's in the equation and replace them with v sub naught over g, which is what we determined before. So the distance equals v sub naught times v sub naught over g minus 1/2 g, and then t squared is v sub naught squared over g squared. Okay? Now, this g will cancel out with the 2 in the exponent here, and we have d equals v sub naught squared over g minus 1/2 of v sub naught squared over g. And so d equals 1/2 of v sub naught squared over g, or you could say v sub naught squared over 2g. Okay? And that's the distance that the ball will travel before it stops. This is all 8th grade algebra. Now let's do something that I like to do once in a while just to make sure. Let's check the units again. Well, let's see. D is in meters. V sub naught is a speed, and it's squared. So that's meters per second squared. And g is an acceleration, so that's over g, which is meters per second squared. Okay? And so that's meters squared over seconds squared over meters over seconds squared. We have seconds squared in the denominator of each the numerator and denominator. Those go away. And then we have meters under meters squared. And sure enough, the distance that we computed is in the units of meters. Now, there is actually an easier way of doing this particular problem that we will discover when we're talking about work and energy, and I will revisit that problem at that time. That's it for now. Come back to lesson 4 for the last 2 problems in this series.